So let's get started reviewing this 2024 AP Chemistry FRQ. And this work is not endorsed by the College Board, and of course it represents my personal interpretations of these problems. And any comments I make or any solutions I have here have nothing to do with the College Board. And of course, these questions were peer-reviewed by my students, so hopefully they're as accurate as they can be. So let's get crazy and start in order with the first question. All right, so in any case, we're dealing with question 1, and they give us a nice reaction here. And we've got a weak acid, strong base reaction. And in the first question, they basically, from the structural formula below, from this organic molecule, interesting enough, organic chemistry isn't part of the curriculum. However, it's really helpful to have some of that information. But in any case, they're looking to circle the atom with that readily participates in the chemical reaction with sodium hydroxide. They're really asking for, in that example, for the most acidic H, or the H, or the hydrogen that's going to dissociate as a proton. And of course, that's going to be this proton here that I circled. All right, and as I explained to the right here, one way to explain why that H is going to be acidic or produce, have a Ka that is measurable, is because essentially these two oxygens will provide enough of an electron drift to pull that pair of electrons over to the left here. So as I show you right here, that pair gets pulled over by the two oxygens. Also, as I said, there's going to be a resonance structure with the conjugate base. The conjugate base, because of resonance, meaning that these bonds here will blend together and create a very stable conjugate base. So those are the two things. And I say this, and again, as I go over this, I'm going to be over teaching these problems because I want people to use, especially my classes in the future, to understand the concepts. Okay, but in any case, you're circling, of course, that H there, also called the Ku group in organic acid. So in B, we want the student begins the experiment. We're going to dissolve 10.22 grams of sodium hydroxide, and essentially we're making a molar solution. And so with 10.22 grams, converting to moles, and then of course molarity is moles over liters, we get the molarity to be 0.11. That should be straightforward. And again, if you don't recognize this, this is the molarity formula, moles over liters. So the milliliters have to be converted to liters there. All right, and of course we needed the grams converted to moles. Okay, pretty straightforward there. Okay. I'm maintaining 3 sig figs because my least significant measurement or measured number has 3 in the milliliters of solution. Notice the 500 point there gives you 3 sig figs. Okay, moving on. So on to the next part of number 1. I love titration curves. And I've got a couple of things going on here, but letter C says, use the information in the graph to determine the approximate pKa. Okay, well, we know at half equivalence, the pH equals the pKa, so we should know that at 16 milliliters of base added to this weak acid, we have reached the equivalence volume, right? So it took 16 milliliters of that solution of sodium hydroxide to completely neutralize the acid, okay, in the beaker or flask below the burette, if you're going to use a burette here. Any case, so if it takes 16 milliliters, then 8 milliliters would be the half equivalence point, and you should know the pH equals the pKa here because the amount of conjugate acid and conjugate base is equal. All right, so any case, knowing that it's 8, I have a little blue line here, and I got this point here, and if I move over, I'm guessing and approximating that the pH, when the volume of base added at half equivalence is 8, is approximately 3.9. And again, that is when the pH equals the pKa. All right, and that's why we get 3.9 there. And for those that don't know why that's the case, is because the Henderson-Hasselbalch pH equals the pKa plus the log of the conjugate base, or the concentration, over the concentration of the HA. At half equivalence, all right, this goes to 1, or I should say the log of 1 is 0. So this goes away, and that's why you have this at half equivalence. Very, very common question and one that a lot of people get wrong. I don't know why. Okay, the next question is something I really, really like. One of my favorite questions on the AP here, on the FRQ. So in letter D, or 1D, the preceding diagram represents the relative amounts of major species in a sample of the solution in the flask at one point. So they want you to draw an X on the diagram where the reaction would be represented by this diagram. So very simply, if I look at the diagram given to me, I can see that there are 4 weak acids and 2 conjugate bases added, and now I know I have a buffer solution because I've got conjugate acid base pairs. But, okay, where do I put the X? Okay, well, we've had a lot of questions about this, at least with my class, and they think because there is far less conjugate base or more conjugate acid in this or at least in this point, some argue that it's going to be below the half equivalence point, that they'll accept any X below the half equivalence point. But I suggested that because they gave us this diagram, the AP readers are not going to accept any X below, and you should understand at half equivalence. Okay, you're at pH equals pKa, but here we have more acids. We're not quite at half equivalence. So in any case, looking at this picture, okay, and notice it's a 4:2 ratio, we can use the Henderson-Hasselbalch right here and solve for the pH, and that's what I did on this side. So I took the pKa that we just got, I got the log of 2, log of 4, okay, did the math, and I got a pH of 3.6. And not easy to identify exactly where 3.6 is on that graph, but there might be some wiggle room. I also thought about it this way, which I think that's why I like the problem. There's a couple different ways to do things. If there are 2 sodium pluses here, here's 1, okay, and here's 1 and here's 2, okay, where did they come from? Well, they came from producing hydroxides. Remember, the hydroxide was delivered by the sodium hydroxide. The hydroxide's not there in our drawing because it was, well, neutralized into water, which means 2 hydroxides in this drawing annihilated or neutralized, okay, 2 weak acid molecules. That's why there is 1 and 2, okay, conjugate bases there. They were made by the stoichiometric relationship of 2 hydroxides being here. So that would mean that we started with 6 HA molecules. Okay, because there's 4, right? There's 4 of these weak acids here, and 2 of them were driven by the hydroxide. I say driven because it's not a equilibrium, okay? It was a completion reaction. All the hydroxides that were dropped at this point were neutralized by the acid, and so we recognize the fact that there should be 2 more. So if there's 6 weak acid molecules, again, this is a model, okay, originally, and now we have what? 1, 2, 3, 4, okay, you could see that 1/3, because 4 out of 6, right, is 2/3, so 1/3 of the acid was neutralized. Okay, well, what's 1/3 of the equivalence volume? I got 5.4 milliliters. And then I just kind of had fun with it. Again, this is more work than necessary to do this, but I'm just kind of teaching the problem because I really like this problem. So if you just make up some numbers and make this 1 mole of acid, we don't know the molarity of the acid, but if you added 1/3 of the moles, this is kind of like what I'm trying to show you here, you can see that this goes to completion here. It's a limiting reagent, and of course we're going to be left with a 0.66 to 0.33, which is a 2-to-1 or a 4-to-2 ratio, which is what the drawing is showing you. So 5.4 milliliters is a 1/3 equivalent. So if you want to find the best way, I think, to find that point, you could have found the pH through the Henderson-Hasselbalch, or find 1/3 of 16, which is the reason I put the X there. Interesting to see what the key will be there. Okay, and sometimes they don't divulge much in their keys and give a blanket answer, but to me, there's a couple different ways to go about this. And both of them give you the same general area. I do believe that X would have to be on a particular point, not just below the half equivalence point. All right, moving on. So we're going to move on to this question here. And what they're saying, this part of the question, is that in the first experiment that we just looked at, or at least the titration curve below, we had this amount of mass of NaOH, and we're going to double that mass, which means we're doubling the moles. And if we know the equivalence volume is 16, okay, for the first titration with the half as much moles of base, then if I have twice as much base that I'm titrating the same acid with, it would require half as much. So that's why my equivalence point for my drawn curve here is at 8 milliliters. Okay, I'm starting at the same position. I'm going to end at the same position because at the final pH we're approximating actually the actual concentration of the base. But the most important part is to recognize that our equivalence volume is the same, and so should our pH, generally speaking, if you can best do that. All right, moving on. So number 3, okay, let's get up close and personal here, is a calorimetry or a thermal equation. And generally speaking, we're going to measure the heat exchanged in a calorimeter with this neutralization reaction. Neutralization reactions are exothermic, but if we didn't know that, we're coming up with that with the data, because we have, in this case, 2 solutions. They give us the densities of the solution. Because we're starting with milliliters, we need to know that, hey, it's mass of the solution here. Right away, we know the Q of the reaction, which we can't measure directly because we can't put a thermometer onto a reaction, is equal to the negative Q of the solution. So we're going to use the surrounding solutions to get information about. That's kind of what calorimetry is about. Any case, so we need the mass of the solution, specific heat of the solution, change in temperature of the solution. Well, 100 milliliters of both solutions gives us 200 because they're saying the density is 1 gram, okay, per each milliliter, just essentially the same as water. So any case, that's how I got my 200 grams. They gave us the specific heat of the solution, which approximates water, and then we have temperature final minus initial. And I write that there because I want people to realize that, hey, this is going to be a positive temperature change. It's not the absolute value. Because the Q of the reaction is negative Q of the solution, I'm carrying this negative all the way through here. And even though I believe that the College Board would accept a positive or a negative Q of the reaction, it's really good practice to keep that negative there. Remind yourself that that's the energy lost. And it's really important because the next question, they want you to solve for the delta H, which is a state function, right? Path functions like Q's, all right, dependent upon how much of the item you have, where delta H is a state function, which means we're going to do the energy per some amount that's involved in the reaction. So in this case, the chemical formula and the stoichiometric ratio of the lactic acid and NaOH were 1:1, and they both had the same molarity and the same volume. So quickly, molarity times the volume gives me, of course, the number of moles. And delta, and they're telling us to find it in kilojoules per mole of the reaction. If I had a mole of this reaction, because the stoichiometric coefficient of the acid and base are 1:1, I have 1 mole of lactic acid. So any case, in this case, I got 0.05 moles. So I know it's a coefficient of 1, so I'm going to keep that 0.05. So in any case, we know that 0.05 moles was given to us, and we're going to put that underneath. We're going to take our Q, which was negative. Don't forget, if you didn't put in the other problem, you better throw that in here. That's why I always suggest maintain your negatives. Convert to kilojoules, we divide by 1,000, and we get our kilojoules per mole. Without the negative, this will be wrong. Okay, this is an exothermic reaction because the temperature change in the calorimeter, okay, increased. Temperature final was larger, okay, which is screaming to you that energy was released from the reaction. That's why you better get a negative delta H. So a lot of questions here on FRQs are trying to come up with how much energy per amount. This was kind of going backwards in that we're trying to find the actual delta H of the reaction if we had a mole. Now we don't have a mole, but we had 0.5 of a mole, and we took whatever energy we had per 0.5 of a mole, and doing this math, we actually are coming up with, the tabulated value per mole. All right, so that's how that works. And moving on, next question is a lot of questions on here where we're answering questions. The student claims that the heat is lost from the calorimeter. Okay, would the molar enthalpy of the reaction, the delta H that we just found, be smaller in magnitude than the actual? Do you agree or disagree? Well, I agree here because, hey, if energy was lost by the reaction, the neutralization reaction, to the environment, that means that it's some energy that the water, or at least the solution, did not absorb. So there, in my opinion, the temperature change would not be as large. So I agree because, and again, to explain and justify my answer, usually these kind of questions are given when you have a known and some experimental. Here, I guess they're asking more of how could that happen? So I agree, it's a great possibility because of entropy and the laws of universe. It's hard to maintain heat it's hard to have a closed system, right? So some energy is going to be released out of the calorimeter. Therefore, the change in temperature of the water is going to be compromised and be lower, and that, of course, eventually leads to a lower calculated thermal amount of energy released and such. So that to me is pretty straightforward. I was actually surprised to see that kind of an easy question. Okay, so next question, and I was surprised across the board with this FRQ in general. So number 2, all right, we've got another acid-base reaction, loving it. And all they want you to do is, given the moles of the CO2, they want you to convert, 2 grams. Wow. Okay. Been doing this many, many years, and they're giving you a point for changing moles to grams. That's crazy. But in any case, take it where you can. All right. I came up with a formula mass, and I went that way. Now, the next thing, 2AII, is a gas law question, where they wanted to take, that moles that was given to you and convert that into how much liters of gas would be collected, at the conditions they gave us. Don't forget that we have to be in Kelvin. And of course, another good thing to notice here is that you're using the gas law constant that has atmosphere liters mole Kelvin. Some people are interchanging the wrong gas law constant, has joules in it. So you want to make sure that your units cancel because we're after, in this case, liters. So in any case, you had to convert your temperature to Kelvin, and it's pretty much a straight plug-in. I always am wondering, that's a straightforward. They gave you these moles, and now we're just making pressure. So again, a rudimentary plug-and-chug ideal gas law formula here. Take it where you can, I guess. All right, so B, student performs a second experiment that's identical to the first, except the student grinds the chunks of this solid weak acid and this sodium bicarbonate into a powder before combining with the water. What happens to the surface area? Well, the surface area increases. If you're going to make it into a smaller pieces, there's, of course, more surface area. There's no explanation needed, and that's all I would think they're looking for. Now, II, or BII, is looking for more here. The rate determining step for the overall reaction is dissolved in the solids. Would the time required for the dissolving of the solids in the second experiment be longer or shorter? Well, I would say clearly it would be shorter, because if your surface area in your if the rate determining step will occur faster due to the, put it this way, if you increase your surface area, there is more exposed atoms that can do what? Collide now more effectively. So the frequency of collisions will increase with an increase in surface area that will increase your reaction rate time. So many ways to say it, but really good to look back into your question and read how they want you to answer this. Justify your answer based on collisions. So the number or the frequency of collisions would increase, as well as the effective collisions, due to the fact that you're exposing more atoms to hit each other with an increased surface area. That, of course, will speed up the rate of the reaction, because it's the rate determining step. Of course, that will increase the rate of the entire process. So many ways to speak to that, and I probably wrote too many words, but let's continue. All right, and moving on, II says, when the reaction rate is complete, will the volume of CO2 at the end of the experiment be greater than, less than, or equal to the volume at the end of the first experiment? Well, if both experiments are using the same initial amount of reactants and they're both going to completion, then you're going to produce the same products. It'll take you longer for the reaction that reacts slower because of a lower surface area, but you're going to have the same amount of products at the end. So that's, again, that's another surprising one there, II. All right, so here we go with another question, and this one got me a little bit in terms of what they were looking for. I know they're looking for the limiting reagent. They're giving me 2 trials 3 and 4. And they're saying, based on the student's data, identify the limiting reagent trial 3. When I look at this, I see that in trial 3 and 4, the amount of mass of my acid stays constant, but my base is increasing and the amount of products increases. This tells me that this is my limiting reagent. Okay, the reaction is limited by how much of this chemical. And so could they accept you just discussing that? But if you notice, this is a problem with me. The way I read the question is that we're using 3 and 4 to make that type of analysis, not just 3. I don't know if I'm reading that incorrectly or not. So I did the old-fashioned thing is I converted them to moles. Yes, it took some time here. Using I had to get their formula masses first, and then I did a Stoich table, okay, whatever you guys call it, and I put the values in. I reminded myself that in the balanced chemical reaction, there's a coefficient of 2 here, and clearly with that coefficient of 2, all right, now, I don't think I need to explain the table, but your limiting reagent is clearly going to be sodium hydrogen carbonate, okay, and you're going to have some excess here. So you certainly can do the math. They didn't say make a calculation, said justify your answer. So I'm just kind of stuck on why they said trial 3. You know, looking at it and eyeballing it, trial 3 to 4, it's clearly sodium hydrogen carbonate is going to be the limiting reagent based on the data there. But why stuck on trial 3? That's the one that kind of gets me. Maybe I'm just not seeing it right. But in any case, I think somewhere, somehow, I got this question right. All right, and I'd be interested to see what they put there. But yeah, the limiting reagent is the sodium bicarbonate. Okay, whether you're, in my opinion, reading from that data or you're calculating. They didn't say make a calculation, just justify. So that's pretty wide open. All right, moving on. If the reaction has a value of delta S that's greater than 0. So we're saying that the entropy of the system is positive. Okay, using particle level reasoning, I can't say enough. You've got to answer these questions based upon how they want you to. So you need to talk about how particles, and when we're talking about entropy in particles, we're talking about degrees of freedom, right? So whether that be different phases that can have more freedom like gases, or just more numbers of particles that come from a lower number of moles of particles. Any case, when I look at this reaction and I rewrote it down here, okay, some people might be tempted to say there's 1 or 3 moles of particles because there's a 2 here coefficiently, but that's 3 moles of formulas. We know that this is a weak acid, so it's going to stay together, but this is a salt that's going to break apart into two particles. So for 2 moles of them, that's going to be a total of 4 particles, so a total of 5 particles on the reactant side. And if you do the same kind of analysis on the product side, you can see that, hey, CO2 is molecular, it's going to stay as 2 particles. Water is molecular, it's going to stay as 2. But hey, this salt of that weak base here, or the salt of the conjugate base, all right, is going to have 3 particles, right? 3 sodiums and that ion there. So it's a 5 to 7 increase. I don't know if they're going to get crazy with that. But the bottom line here is that there's an increase in the degrees of freedom because there are more moles of particles in the products than reactants. Specifically, we're producing 2 moles of gases that originally we did not have. And gases have more degrees of freedom, okay, than aqueous solution. Obviously, gases have that freedom. So the idea that we put 5 to 7, would that be enough to say that there's more moles? Maybe. I really think the question is about the fact that you need to demonstrate that you understand that we're producing 2 more moles of gas that wasn't there before from a original scenario that had aqueous ions. And gases, of course, have much more degrees of freedom than aqueous ions. I think that's what they were about there. All right. And you certainly could, read what I'm doing here. All right. So that's how I think they were after that idea that we are producing a gas from aqueous. I think they're looking for that more than the moles, but it'll be interesting to see. Okay, so the next question, and classic Regents AP question here. So the student claimed that the reaction is thermodynamically favorable at all temperatures. Okay, and I said I disagree. And reasoning is because I recognize the fact that although the entropy of the system is favorable, the entropy of the surroundings, or the delta H of the system, is unfavorable, meaning, hey, it's endothermic. So if you do your math plus your negative, you can see that this is going to be a negative expression, okay? Which is good. That's a favorable thing because we want to make delta G to be negative. But so we're going to need an increase in temperature to drive this T delta S to be more negative, all right, to make to overcome this positive here from the entropy. And again, many ways to say that. I don't know if I said it very eloquently, but the temperature needs to be increased to increase the negative value of T delta S to overcome the positive delta H to make the delta G negative or be spontaneous, something along those lines. But definitely disagree. This is, of course, an entropy-driven reaction. All right. Sometimes I call it the sometimes rule. All right. Now we've got a diprotic acid with 2 Kas. And then all they want to do, they want the pKa of the acid. Little p, of course, means what? Negative log. So negative log your K2. So from the data, the K2 is 8.5 times 10 to the negative 7. And using your calculator, you should get 6.07. It couldn't be any more straightforward than that. And then we have a question that people I know struggled with, okay? And a lot of my students did, okay? Although we've done the problem, it's not something we do a lot of. So this is a buffer problem, and we're looking for the ratio, okay? And very simple, you know the pH that you want to buffer at, okay? That was 7. We know the pKa that we just got, and they want this ratio. This is the ratio that I put in black here, which is conjugate what? Conjugate base over conjugate acid. So don't fall in love with what those numbers are. You're going to find that total number. If you found it to be 10, it's 10 over 1. Okay, so whatever number you get here is a ratio. So very simple. With the known pH, the pKa, we can solve this ratio as your x. So this ratio here could be your x if you want, if that helps you mathematically. And in any case, you do the math and you're going to come up with 0.93 equals a log of that ratio. And some people get stuck here. And as we've seen in the equilibrium calculation delta G, when you have an e to the x on one side, you have, natural log of some value, like natural log of k, right? Remember, natural log of k equals the delta G and everything else in between. Okay, to get rid of this natural log, we do e to the x of both sides, okay? Which does what? Which gets rid of that. So we're going to do 10 to the x of both sides, or 10 to the 0.3, 10 to the log of the ratio, and that gets rid of the logarithm. And so we get 10 to the 0.93, put that in your calculator to get 8.51. That confuses people. It's 851 over 1, right? You're saying that this value is 8.51 times greater than that of HA. So it's a 8.51 to 1 ratio. You wouldn't need that. That would be suffice, okay? So not that difficult. It's just that for many people, they haven't practiced that. And it's not a common problem you see on FRQs, but a one that we should definitely go over when we talk about buffers. I'm sure most people did, okay? All right, moving on. So we're on to question number 3, and my gosh, they asked for oxidation numbers. Surprise, surprise, surprise. A standalone element, of course, is 0, whether it's bonded to itself or not. Protons equal electrons. For atoms, it's a 0. And of course, the silver is +1. A lot of students, including myself, sometimes confuse the overall charge. And you say, why do I talk about an overall charge? Well, because, hey, if sulfur is -2, whole thing has to equal 0. It's an ionic compound, so it's +2 overall. But there are what? 2 silvers. So each silver is +1. We're after that individual oxidation state. Okay? All right. Any case, moving on to another, I think fringe. Certainly oxidation numbers aren't a fringe, but I think this question is kind of a fringe of the curriculum, talking about alloys. And any case, explain why the silver, and so this is the idea that silver and copper make sterling silver. A little bit of silver is mixed, a little bit of copper is mixed with the silver. They're giving the atomic radius, and they're asking why this is a substitutional and not an interstitial. So my answer basically talks about the idea that the atomic radius are very similar, okay? And in doing so, we should understand that if we've got a crystal lattice formation, we could have a body-centered or a face-centered formation, okay, that a copper would be able to fit in this position here because it's about the same size. So as this crystal lattice, continues on with a regular three-dimensional arrangement, the next atom should be able to fit into that position because it's about the same size. Interstitial is when the atomic radii are so far different from each other that the atoms can exist in between. It's kind of like how carbon can get in between iron to make steel. Okay, so in any case, that's the idea that they were similar enough that they could fit into each other's, or in this case, copper could fit into silver's crystal lattice position. Whereas interstitial would mean that the sizes of the atomic radii would be so different they fall in between. Okay, so that's that. And again, if you got one of these wrong, okay, so be it. Okay, it's not something that you spend a lot of time on, I'm sure. That's why I call it a fringe question, but this one's not. Using principles of atomic structure and Coulomb's law. So I underline that to remind everyone that that's how they want you to answer the question. Why does silver have a larger atomic radius? Well, larger atomic radius. Well, if you look at copper, its outermost electrons exist in the n equals 4, principal energy level. While silver, underneath copper in the same group, has the same valence electrons, but is in the what? It's in the 5th principal energy level, or n equals 5. And that right here, me talking about principal energy levels, or n equals 4, n equals 5, those are synonymous terms, I am covering the principles of atomic structure. So I'm telling you that silver has a shell of electrons that is farther away than copper. And now we're going to go to Coulomb's law. And Coulomb's law is about the size of charge, or in this case, distance. So if electrons are farther away from the nucleus, then they're going to have weaker Coulombic forces because Coulomb's is based upon size of the charge and distance between positives and negatives. Okay, so this is a classic AP question here. Moving on. All right, so in this question here, they are removing the tarnish from the silver. We subtract before and after to get the amount of tarnish, or in this case, silver sulfide. And then, of course, what we're doing is finding how many grams of silver we're actually removing. Straight, stoichiometry. I am converting to moles of silver sulfide here. And then, hey, aren't there 2 silvers per every 1 sulfur? That's what I'm doing here in this ratio. They just wanted moles, okay? So for every 1 formula of silver sulfide, there is 2 silver atoms. All right. I think you should continue on to grams, but in any case, that's what they wanted. So that should have been fine, right? Subtracting before and after, converting to moles, and then doing the ratio. This could be a 2-point question where they give you 1 for getting to this point and the 1 for the ratio. Who knows? Okay. I haven't really worked that out. All right. So I got a lot written here for this next question because they're talking about rhodium plating. Rhodium's a metal, and plating means that we're going to take an ion and make it a solid. And we should recognize plating or electroplating or electrolysis is a non-spontaneous process needing a battery. But if we didn't pick up on that, all right, you probably should have picked up that if we're going to plate rhodium, we need this reduction reaction. Because these are both written, these half reactions given to you are both written as reduction, as standard reduction potentials from a table, then the other one's got to be flipped. And if you flip the reaction in thermodynamics, you're going to flip the charge. So this is going to go negative. Okay? So you got to flip the second one. If you didn't understand electroplating was non-spontaneous, and then you're going to get negative volts, therefore you're going to flip the one that will make it negative volts. That's one way to look at it. For a lot of these problems, they're voltaic cells, and you flip the one that makes it positive. Kind of silly. But there's enough clues here to know that, hey, we're gonna do this reaction here. That's the whole purpose. So that reduction has to occur, which means the other one is oxidizing. So we have to flip that one. And that's what gets us here. Wrote this reaction as is, and I flipped the second. And through all my work here, I recognize that there was 3 electrons that are being reduced and 4 being kicked out in oxidation. Least common factor in 3 and 4 is 12. That's why I had to multiply this by 4 to make this 12 electrons, because the goal here to get an overall reaction is, of course, to balance your electrons. Balance your electrons, you automatically will balance, okay, your charge in your reaction and your overall reaction. So I balanced my electrons. I distributed this by 3 times, because 3 times 4 over here is 12. these 12 of electrons here will cancel, and then I add everything up. And I also do a little check to make sure I did this right. I like to check the total charge. 4 times 3 is 12. Water is neutral, so it's 12 on this side, and it's plus 12 on the other for similar reasons. Okay, and then they want the net potential. Okay, standard cell. And very simply, because I flipped the second right here, I flip the sign and add them together. I do not multiply by how many moles across here for this value here. These are measurements about how well and spontaneous that certain compounds are able to get reduced. Okay, that's where this comes from, or oxidized if you flip the sign. All right, moving on. I think that was pretty darn straightforward, really. Okay, thank the heavens, or if you don't believe in anything, no heavens, for that question. You should have cashed in there. Okay, next one, E. All right, so next one, I, Captain. They want to know if this process, or explain why this process needs power. Yeah, electrolytic cells, electrolysis, they need a battery or a supply source. So I said E0 is negative, as we see, and delta G is positive. But I can't explain that because delta G is negative N Faraday's constant E0 cell here. And what does that mean? Well, if this E0 cell is negative, and of course we have a negative in the reaction, that makes delta G, negative and negative, become a positive. And a positive delta G we should know is non-spontaneous. And non-spontaneous reaction requires a constant supply of free energy. I don't know how much more you can do there. I probably overdid it there. They're probably looking for a statement. Okay, negative volts equates to a positive delta G. That's probably what they're looking for. But I'm using this to teach. Oh, I love these questions here. Okay, I know some people won't get to the chance to teach this at the end of the course, but okay, we've got 2.8 grams of rhodium. The first thing I do is I convert it to moles of rhodium. Then, with the moles of rhodium, I have found the moles of electrons needed to get rhodium made from its ion, right? This ratio here, 3 to 1, notice the rhodium's on the bottom, okay, is due to the half reaction. Now I have moles of electrons, okay, it's moles of electrons. Now, timesing by Faraday's constant, I get the total charge of the electrons using Faraday's constant. Now, using the ratio from the amperage, okay, I want to get rid of coulombs, and there's 2 coulombs per second in the amperage when they measured it, and I get total time. So really not that difficult of a problem there, and I would assume that there's going to be a couple points here somewhere. But in any case, there's the answer. Notice I had started with 2 sig figs, I ended with 2 there. Any case, moving on. All right, so here comes the 4-point problems. All right, and they want you to measure the temperature, it's the highest temperature of the water, but 38.5 is what I get, and of course people forget that we have to measure the guess. Okay, got to understand that we've got a guess here. So I'm guessing it's halfway, so 38.5. All right, all numbers on a measurement device plus the guess, and that includes all significant numbers. All right, now back to the problem. I can't believe this. Now, the final temperature was 38.5, and it's higher than the initial. So with this particular diagram, they wanted you to answer, or at least draw arrows here on the after. And I really can't believe this is a question. What we know is at higher temperature, we know temperature is proportionate, okay, to average kinetic energy. So at a higher temperature, on average, these molecules would be going faster or moving at a higher velocity. So all I did was make every arrow a little bit longer. What I didn't do is make all these arrows the same size. That would be wrong for sure, because the particles are not going to change in a way that every particle has the same exact speed. That doesn't occur, right? It's the randomness nature, the Boltzmann distributions of particles will never occur that way. So you needed to just extend these lines, make them a little longer because they're going faster, to still demonstrate that the average is increasing, not they're all becoming the same speed. Okay. Again, thank the Lords or the heavens or nothing for that question there. Here's another thermal equation. Now, assuming that the metal transfers 2940 joules of thermal energy to the water, calculate the specific heat of the metal. Okay, so we need to understand that the metal, you don't really need this, but you should always write this, the metal that we're measuring is equal to the negative Q of the water. All right, any case, you don't need that here, but I kind of do that. So the metal, what I do tell people to understand is that when you do these thermal equations, they're always on the same team. So Q of the metal is the mass of the metal, specific heat, and change of temperature. Some people are mixing and matching with the water. Keep your Q's on opposite sides of the equation. That's why I like to write Q of the metal is negative Q of the water. Any case, I'm going to solve for C. I know my temperature change, my mass of my metal, and my Q here. Notice my temperature change is negative, and my Q is negative, and of course it comes out positive. Specific heat can't come out negative. Again, too much work with the negatives probably, but it does remind students that we're always on the same team. We're going to solve for the Q of the metal in this case. All right, any case, it's a plug and chug. The biggest mistake I think people would make here is that they would use the initial temperature of the water. Again, we're talking about the metal, so we need the temperature change of the metal. The metal was sitting in boiling water, and then it reached thermal equilibrium with the water. So that's the biggest mistake I could see happening. And I guess use your units to see, make sure you got the right ones. Any case, that's my answer there. The next question is D, and they want to know, hey, if I do this same experiment with the same energy and the same size block, but instead of using the metal that we use, don't know what it is, we used aluminum, and knowing aluminum has a specific heat of 0.897, which is higher than what we get here from this calculation, how would the temperature change? Okay, and so the temperature change would be less. With a higher specific heat, you require more energy to change the temperature. Now remember, look at the unit, joule per gram per degree Celsius. So this is the energy it takes per gram per degree Celsius. So if you have a higher specific heat, it takes more energy to change 1 gram of water 1 degree Celsius. So you could say a bunch of different things here, but I just said the magnitude of the temperature change of the aluminum will be less than that of the metal in the first experiment because aluminum has a higher specific heat with the same mass and energy transferred. And I did the math just to cover all bases here, and I solved for the change in temperature of the aluminum given that specific heat, and you can clearly see that it's less than the one from experiment 1. And then I stated again what specific heat is again. And again, I'm covering my bases here, but they would definitely take the math and the comparison, and something along the lines of if the mass and the amount of joules were constant, a higher specific heat would have to lead to a lower temperature. Okay, any case. On to number 5, the second 4-point question. Not a big fan of this question because I know a lot of people probably looking at this and see gases, so they think that as the teachers are reminding them that you need parentheses and a little p for partial pressures. That's true if it's Kp, but this is Kc, all right? So definitely brackets for molarities. Gases can have molarities because there's moles per volume of the container they're in. So I can see a lot of people using brackets here. And I'm not a big fan of that. This late game in the test, you're going to do that. But hey, whatever it is. So that's what A is. Products over reactants, coefficients become exponents, solids and liquids do not apply. Now here comes B. This part I do like. So they gave you a Q of the reaction to be 0.67. Of course, Q is a snapshot in time when you're not at equilibrium. And the diagram was incomplete, and they wanted you to draw in what's missing in terms of the HI molecules. Okay, so I know for me right away, I know that Q and K, P, Kc, Ka, any equilibrium constant have the same formula. So even though you probably have never done this, we're going to solve for what the other value is in the Q. If you know the Q is 0.67, and from my diagram, I've got 3 what? I've got 3 hydrogens. I've got 2 iodines. What does that mean? Well, I put that into my equation. Remember, these are particles, but these are moles of particles. And if I pretend that this space is 1 liter, that's a molarity. I can do that ratio there. And then I solve for X, okay, and I get approximately 2. And therefore, I drew 2 there. So I know a lot of people got confuddled here by how do I solve this with Q? They forget that Q and K have the same formula. So it's a snapshot in time where you're not at equilibrium. So at that snapshot, exactly how many, what would be the molarity in this case of the X squared, which relates to how many particles in the way that I set the problem up. So in any case, I added 2 there. All right, I like the problem, I really do. Okay, but haven't seen this one type on any other FRQ. All right, moving on, but definitely doable. II is that in this case, in this same problem, they want you to hypothesize an experiment change that could have been applied to the system in the rigid container at time t. All right. They said, though, and I didn't read this carefully the first time, so I'm going to talk about this, but assume that the student did not add more HI to the system. So when I was reading this initially, I said that you couldn't add anything. I think I was thinking of another practice AP that I was reviewing. So what I said is, well, because I know that the reaction is exothermic, how do I explain this? Because this is like a question I've seen in another practice test. Good job to practice test, see as many questions as possible. But because they reported a delta H to be negative, knowing it was exothermic, I know that a lower temperature favors the endothermic pathway. So the forward reaction would occur. The moles of HI, of course, are products. So if it's exothermic and I lower the temperature, their equilibrium constant is going to shift to favor more products, and we're going to produce more. And that's why there's an increase in HI. So I know that's a good answer. The temperature is decreased. But at the time, I didn't think I could accept it because I didn't read as carefully. But obviously, the easier answer is increasing more of your reactants. And since your reactants, okay, are HI, okay, hydrogen and iodide in this reaction here. So you could have, by Le Chatelier's principle, increased H or I, and that would have shifted the reaction to the right to produce that. I originally didn't think you could do that in my head, so I went with temperature. But I like the question, more than one way to get a right answer. Okay, so as far as I can see, that would be appropriate way to do that. All right. I started thinking about pressure in this question too. All right. So, and I realized that pressure is not going to work because there's 2 moles of gas on both sides, and lo and behold, that's the next question. So if you look at the next question, after equilibrium is established, the mixture is transferred to a larger container, which means the volume is increasing. Well, we know volume is inversely related to pressure, so the pressure is dropping. So the stress would be a lowering of the pressure, but that would have no effect on equilibrium because, as I just said before, the moles of gas are similar on both sides, so the reaction can't shift to alleviate any stress there, so it won't do anything. Okay, so the 2 gases, or the moles of gases, are equal on both sides, so we know that there'll be no effect with that stress, as you have learned previously, I'm sure. Okay, so again, not a very difficult explanations here. All right, and then we go with number 6, and we've got this reaction, NO2. All right. Decomposing there a little bit, and we have the two graphs of the rate of reactions, and based on these 2 graphs that were plotted based upon the data during this reaction, explain how the graphs indicate that the reaction is second order with respect to NO2. Well, I said that very simply that, and I think this is important, there's a linear line with a positive slope for the graph of 1 over the concentration of NO2. So the question is, what are they going to accept? Well, they said, I always tell people to look at exactly how they're asking, explain how the graphs. So to me, I need to mention both graphs. So the graph of ln, natural log of NO2, is not a linear line with a negative slope. That's one reason why it's the second order, because that's not the first order. And the graph of 1 over NO2 is a linear line with a positive slope. So therefore, it's second order because it follows the integrated rate law formula, okay? And the way that I set it up is so that y equals mx plus b, right? So this is minus this factor. I just algebraically put it to the side. So you should recognize that second order has a positive slope and needs to be also a linear line. So if you just said a linear line, it's not, in my opinion, good enough. You need to say with a positive slope, because this could be a linear line. Okay, and we could also have a linear line going, in different directions here. So it has to be a linear line, but with a positive slope. All right, that's what the integrated rate law equation is proving. All right. Any case, moving on. So B, real answer, easy question. They said that the rate of disappearance of NO2, that's one of the reactants. I redrew or at least copied the formula there. Okay. is determined to be 6.52 times 10 negative 7. Okay, well, what's the rate of appearance? So this is the rate of disappearance. Well, I don't care about appearance or disappearance, right? Whether you're losing or gaining, it's still a speed in molar per second. The key is the stoichiometry. There's half as much O2 that's made by the disappearance of NO2. So if we know the disappearance of NO2, it's got to be half that of the appearance of NO2. And that's why you just divide by 2. And that's just pure stoichiometry. Hopefully you saw that in your kinetics or your rate law. All right. Any case, moving on. C. Moving on here. So this one's an odd one, and I really like this question. It really makes you think. So they drew the NO2 as a free radical as it is. And then when it removed an electron, they wanted you to draw the Lewis dot diagram. Well, my friends in chemistry here, a lot of people, I believe, would draw this right here. And there's a problem with this. Number one, the octet is not satisfied with the N. N is a second row element, must really have 8. I know there's some examples when it doesn't have 8, okay. But given these formal charges, -1 and +2, could I draw a better structure? Yeah, okay. The oxygen loves a double bond, so this would have a lower number of formal charges. They didn't ask for formal charges, but I'm just trying to explain why the first one is a little bit better. Also, be careful. A lot of these Lewis dot diagrams don't say to show all bonding as dots, okay? So in any case, this N fulfills an octet, and the formal charges are lower. I know they didn't ask for the formal charges, but they could have. That's why I'm trying to teach you everything I could here. So in any case, that's the best structure. And if you didn't get that or you got confused on that, don't worry. It's only a point I would suggest there. Okay. Now, this one you should get for sure, okay? A student makes the claim that the bond angles NO2 and NO2 plus are different from each other. Do you agree or disagree with the student's claim? Well, I agree, because the lone electron in this orbital will repel these electrons somewhat. Not as much if there was 2, but it's still going to repel them. So therefore, the bond angle is going to be a little bit less than 180 for sure, a little bit bent. If there is no electrons in the central atom of nitrogen, as we have it drawn here, there is no electrons to repel these electrons down this way. So this is going to stay linear and be closer or be about 180. All right, so this is about VSEPR theory, how the central atoms lone pair can dictate the molecular, okay, geometries. All right, so that's my answer there. And then we move on to number 7. And real quickly, hey, molarity times liters gives me the moles. And then from the moles, using the formula mass, I get the grams that I need to make a solution. That's important. All right. And so that's what I have here. If you like your beautiful little dimensional analysis, I put that down there. But I tell my students molarity times volume. So they wanted to make a solution using solid NaL, and you want to make a 0.34 molar solution, and you want to make that amount. So we had to figure out the moles, and then of course convert to grams. That's the grams that we're going to have to use to make this amount of this concentration of that solution. The last step, or these 2 steps, I got a lot of people here. What are the steps here? Well, we're going to weigh the 1.99 grams. That's 1. 2, you're going to add these 1.99 grams into a 100.0 milliliter volumetric flask. And then we're going to add water and dilute it. Now, we're not going to add water to the line, because if you do that, the volume that a solid takes up is different when it dissolves. So it's not an accurate way of doing the solution. So what you're going to do is you're going to add these grams, then you're going to add some water, and it's underneath the mark to dissolve this. Once it's dissolved, they're going to swirl the mixture, and then you're going to dilute with distilled water to the mark. I know a lot of people, I saw on TikTok and everywhere else, Reddit, they didn't know what to do with this. And I was wondering what that question was. And it's very simple. You cannot add the solid and then dilute to the mark, as most people wanted to do, because, again, the space that a solid takes up is different than the space that the dissolved ions fit into water. Okay? So that will not get you to the promised land. And of course, we don't fill it all the way up to the mark, then add the solid too. So you had to pre-dissolve it with a smaller amount of water, then what? Stir them, and then of course, once that's dissolved, then fill that solution up to the 1 millimeter mark using a pipette, or eyedropper, in this case a pipette. All right. They always seem to want to use a burette. So this is a typical question that's been popping up in a lot of practice exams. Okay, they just did it a different way, and I really like it. And if you haven't done the labs or the hands-on labs, then maybe this was more tougher than you thought. Okay, but again, if you missed out one of these, it's a point. All right. And then last little question here is chromatography. And we have two spots that moved up from they were initially mixed together in one spot. And clearly Y is separating from X. And they want to know if we did this in 30 minutes, there was a separation if we measure the distance between this spot and this spot. What would that separation distance be if instead of doing for 30 minutes, we ran this for 15 minutes? Well, I said that the separation would be a smaller distance. Okay, and the reasoning is that, first of all, compound Y is more soluble in the solvent, the sodium chloride solution, than X. So it was more similar in its attractive forces. Therefore, it was moving up faster as the solvent moves up the chromatography plate by capillary action. Compound Y had more similar attractive forces, was more soluble. Therefore, it was moving more with the solvent front than X. So it was moving faster than compound X. Therefore, if we wait and cut the time in half, although Y is moving faster, it didn't have the time to separate as much. Probably with more words there than needed. But a shorter period of time would decrease the time required for compound Y, which is more soluble in the solvent than compound X, to move faster. So I'm probably using way too many words here. But clearly Y was outpacing X in terms of moving with the mobile phase because of its, very important in my opinion, it had more similar attractive forces or was more soluble than X. So given more time in 30 minutes, of course it'll be farther away as it's outpacing. And given less time, it would be closer because they all started from the same point. All right, now I didn't say the same point. As I'm saying it here, maybe I needed to add that. I tend to get wordy in my responses here. Interested to see what AP Central will have. So I hope that helped. And certainly these are my interpretations, nothing to do with AP. Good luck with everything.